The SD Ruby podcast is brought to you by New Relic.
Hey, I'm Xavier. I'm going to talk to you about functional programming and in general, and then Haskell to be specific. So, hi, I'm Xavier, Ruby hacker. I've done a little detour into Erlang before. That was my first trip into functional programming. So I kind of drank the Kool-Aid there and got used to a lot of the concepts you find in functional programming. Then I went back to Ruby, and for the past year and a half, I've been doing some hobby projects in Haskell. So I thought it'd be interesting to share. And so, what's our motivation to explore functional programming, right? So the idea here is, how are you going to know Ruby really well if you don't know other languages just as well? You don't have anything to compare. You want a little bit of a contrast there. So you can never understand a language until you understand at least two. So I think that's a good motto to keep in mind when you're going through some of the pain you might find writing Haskell code. So what is a functional language? What makes it functional? So you think about manipulating values and not state, right? So you're not initializing objects and then mutating them. That's how you do it in Ruby, right? You've got this initialize method. It puts it into memory, and then you start poking at it, doing things to it. But here in a functional language, you just have a value. And it's a lot like your elementary school math. You're taking one value to another value, right? And so in any functional language, a function is usually a value. So you can actually pass around functions just like anything else. And it's pretty common that recursion is idiomatic. So usually you have a recursive data structure, or you've got a list or something like that, and you just want to break it down into smaller and smaller components until you've satisfied your conditions, and then there, you're done using it. So recursion, use it all the time. So
what's the distinction there if you're saying a function is a value and you can pass that around? Isn't that state?
Well, no, the function is just a mapping from one to another.
Oh, I see.
Right? So it is stateless once it's made, right? You can call it repeatedly and you'll get the same value out of it, right? That's a good question. So, right. So now that I've described a little bit of the functional languages, who here has written anything in a functional programming language like Clojure, Scala, Erlang? All right, cool. All right. So Haskell, it's a functional programming language, and it does some extra stuff, right? So this is different than Clojure or Erlang, where there it's very much you get runtime errors. So here in Haskell, you're not going to get those type errors. You're not going to get nil method errors that you might get in just about any other dynamic language, right? And Haskell is a research language, and so they chose to make it into a lazy language. So you prepare computations, but they're only done when they're absolutely needed at the last minute. So if you've got a big list and you want to do stuff to every element in the list, Haskell's like, it'll just return right away and be like, yep, I did it. But it hasn't been done yet. It'll be done later when you actually need the value, right? And just a common feature, you don't find it in all the functional programming languages, but here you can curry. So currying is idiomatic. So if you have a function which takes 2 arguments, you can add 1 argument to the function and then carry that around, right? So that's not stateful necessarily. All you're doing is fixing a value to one spot, right? So some of the features of Haskell that really brought me in are the Glasgow Haskell compiler. So that is the industrial grade compiler that, if people are using this in industry, they're going to be using GHC. So it's optimizing, and it's got a really nice infrastructure for making standalone executables and actually making linkable libraries. So for the most part, you can't tell it's Haskell. So if you wanted, you could write a library in Haskell and bring it into Ruby, and it would just look like any of those, C extension libraries you find. And icing on the cake, it's got a library ecosystem, like gem cutter, Ruby gems, or CPAN, right? You can go through this library repository called Hackage, see what people are doing, and you can install them using Cabal. So Cabal is the build system that you use in Haskell, and it's nice. It's like Bundler. You make a manifest of what libraries and what versions you need, and then you can add options for how you're going to build it, and whether it builds a library or an executable, all that good stuff, right? And so Cabal is already the standard. It comes with the Haskell platform, so you're going to have it, and it's going to be pretty easy to use. So in Ruby, we get used to duck typing, right? When you're in Ruby, you get something that comes in, and if you're a good Ruby programmer, you're going to say, oh, do you respond to string? Do you respond to integer? Can I call reverse on you? Those kinds of things, right? So, if it walks like a duck, quacks like a duck, it might be a duck, right? So, on the other hand, you've got Haskell, and Haskell is rigid, right? So it's not rigid in the way that you might expect. It's more like all the pieces have to fit together. So, Haskell does have types, but the compiler will help you out, and you don't have to specify everything. But if your program does compile, it's going to look a lot like this, and all the little pieces are going to fit into their little spot. So, you always have to do a hello world, so make a little introduction, right? So, it's pretty standard, it's not too bad, only 3 lines. It's not puts that you get in Ruby, a little bit more, but it's pretty complete, right? So, I said it's compiled, right? But there is a interpreter, right? And it comes with the platform. And so you can make scripts, just like in Ruby, right? And the big deal here is you just have to define main, right? So you define a function by just doing a symbol and then equals, right? And we're going to ignore do for now. And then, this is a list of characters, also known as a string, right? And then here's a little trick. Space is the function application. So when you want to apply a method in Ruby, you say object dot whatever, right? But here you say space. So put strline is going to be invoked with that string argument, right? And it'll do just what you expect. It'll print out to standard out, hello SD Ruby, right? So pretty easy, not too bad. Hopefully not too scary. Right, so here are some types, right? So I'm going to be using this syntax in the rest of the slides. So the way you read it, on the first one you say 3, and then the colon it means is of the type, and then the type, right? So 3 is of the type integer, the string 3 is of the type string 3 is also type list of char, right? And then you got your floats, your booleans, and then, containers of other values. Right? So, a good way to learn Haskell is to start over. So you've got a big standard library that does all the cool stuff you want, but, it's kind of fun to just re-implement stuff. And you'll find that what you're writing looks a lot like how the standard library is written, because a lot of GHC is written in Haskell. So you can always check up on your work. Right, so we're going to start with Boolean, right? So pretty straightforward. We say the type, right? Boolean. So data is a keyword, then you give it the type, right? And then you get your value constructor. You got your other value constructor, right? So what we're saying is that a Boolean can be true or be false. That's it. So the nice property here is that we're not breaking the type hierarchy that you get in Ruby, because Ruby does a weird thing where they say true class and false class. It's really weird, but that's how they do it. So we're going to define some basic functions to use a bool, right? And so what I'm showing you here is destructuring. So I'm saying not is of the type bool to bool. So it's a function. You put in a bool, it's going to put out another bool, right? That's what you expect from not. So what you can actually do is you can use that value constructor right inside of the function definition, right? So you say, not true is false. Not false is true, right? So it's just like a high-level declarative interface. You put your value right in there, and then you can start using it, right? And then we can also define and, right? So and is a little bit more complicated, right? And is of the type bool to bool to bool, right? So you're going to give me a bool, then you give me another bool, and then I'll give you your final answer, right? So here, more destructuring, right? So and is actually an infix operator. So it looks kind of weird that I've put and in brackets, but you don't need to use it that way. You can actually use an infix. So here, I'm just using an infix in the destructuring. So you see the false and blank. I don't really care what it is, right? That's how and works. You don't care what the second thing is if the first thing is false. It short circuits. So I'm expressing that right here. And then we've got true, and if it's true, the thing that matters is actually the second argument. So I'm just going to return it. So that's how you do and. Okay. All right. So you saw a little bit of a simple data type. It was very straightforward. True or false. I started using the values in a function, getting some work done, just making some computations. And here, we're going to start making a container, right? So how would you build a container in, like C or something like that? You would allocate memory, and you would keep track of elements in the array, or you'd make a linked list or something like that. But here, you can actually do it just by declaring a recursive type. So data from before, and then list A, right? So we're not going to talk about the A just yet, is nil, right? Just like in Ruby, is it empty? It's nil, right? So either it's an empty list or it's cons A and then a list A. So this syntax might look a little hairy, but essentially what I'm saying is that a list is an element with another list, right? So that's going to be helpful when we are doing some destructuring later. Right? So, typical phrase to use in functional programming is cons. So you cons a value onto a list, right? So cons is of the type A to list A to list A. So what I'm saying is, you give me a value, you give me a list, I'm going to give you a new list. And hopefully it's got that value on it, right? So when you come in and you call cons, what I'm going to do is I'm going to construct a new cons using that one value plus that list. So if you're looking at how the type signature looks compared to the arguments, you'll see that A maps to X, and the list A maps to X's, right? And then we just build it, and that's it. X's could be nil, or X's could be cons A, list A. It could be another list. But for the sake of what we're doing, we're just building one more layer up in this recursive data structure. Right? So let's apply this a few times, right? So, in Haskell, I can just say nil. Okay, cool, it's nil, right? But then I can say, cons 1 to nil, and then I get this value back that is cons 1 nil. And then to keep it going, to keep that recursion going, to kind of show you how that works, right? I do cons 2 to some list, and then I do cons 3 to another list. And that's a good way to think about it. It's just, you only think about those two parts. It's just a recursive data structure. All right, let's do something to it, right? So, you know, a good thing to ask a list is how long are you, right? So you get a list coming in, and you want to get a number back. So here's our function definition, or our function signature, right? List A to integer. So I'm just repeating the data definition so you can see what it looks like. And then we're going to use destructuring again to break down this data, right? So this is called, you know, type-oriented programming, right? You know all the possible values of your input, right? You know that this thing takes a list, spits out an integer, so you know that you only have to cover those two cases for a list, you know, nil or cons another list, right? So what we're going to do, simple recursive definition, right? So a good way to think about how this looks right now is kind of like a case statement. That's kind of how it breaks down. But it is just a high-level declarative thing. So it's going to evaluate that first function, and it's going to try to put that list into that first argument. Right? So if that first argument is nil, then we're just going to say 0. It is an empty list. There are no values in it. It's nil. Right? But if it does have something in it, we're going to break it open. Right? We're going to take the cons keyword out. We don't really care what the value in that list is. We're not using it. So we're just going to put it in the bit bucket, and then we've got the rest. But we know that we've unpacked it once. So we're going to say 1 plus, right? And then we're going to recurse on the rest of the list. We're just going to say, okay, 1 plus rest of the list. Just keep going. Let's do that, right? So, you know, if you were to do it this way, this is how it would like unwrap itself. You know, this is kind of how I think about the computation being performed, right? So you're busting apart these parts of the list until you get it reduced all the way down. So, you know, when you're in Ruby, if you have a list, every single one of those values that's in there has already been computed, and you know that it's there and you can access it. But in Haskell, the list, you know, we're building this recursive data structure, and you know, the Haskell implementation can choose to not actually evaluate anything. It can say, I'll do it later, right? Because we're not doing anything that touches I/O. We're not printing to the screen. We're not doing anything. So Haskell feels safe to just defer. It'll just say, I'm going to do it later. You know, I don't know if you want all of these values to be computed, so I'm just going to do it later, right? So, I'm going to show you zip width and a lazy list. So, here's something cool. It's 1 dot dot. So what I'm saying is, okay, Haskell, I want a list that goes from 1 to infinity. And Haskell's like, cool, I can do that. Not a big deal, right? So this is the signature that it's providing, you know, and it's a little bit more complicated, but you know, it figured this out for me. I did this earlier in an interactive Haskell session. I was like, you know, I forgot enum and num. You know, I know what they mean, but I forgot about them. I didn't need to know them. I just needed to ask for the type of the infinite list, right? And the little arrow says, oh, it's a list of t. Okay, cool. All right, so here's another function definition. A little bit more exciting still, right? So you look at it, and you see a lot of arrows, and you're like, it's kind of ugly, right? But you see a bracket, and it's there to help you out. Those brackets don't actually need to be there, but I'm very happy that whoever wrote this library did. So it's saying that you need one function first that takes A to B to C. So it takes in, you know, some value A, some value B, maybe to a C. And then you're like, okay, I can do that. And then it says, okay, you want a list of A's and a list of B's. And you're like, oh, that's kind of convenient, right? I've got a function that goes A, B to C. I'm going to have a list of A's and a list of B's. Sounds like I got everything I need to kind of slap things together. So, yeah, show that again. Okay, so here we are, right? And so I'm showing you zip width again, and then we've got our plus. So that's plus just like, you know, any other language, right? Takes A to A to A. So 1 plus 1 is 2, right? 1 and 1 have to be the same type. Right? That's what Haskell is trying to say. And so zip width takes the plus, right? And it takes the list 10, 11, 12, and then an infinite list. And it's going to zip them together. So what it's going to do is it's going to take the parallel elements of the list, kind of put them together, and give you a new list. Right? So, right, it's just going to say 11, 13, 15. And to kind of help you see what's going on there, I can do a zip width that doesn't map to a new value, but kind of shows you the stuff. So I'm using, tuples here. I'm just saying, oh, that first element was made with 10 and 1. That second element was made with 11 and 2. Third made with 12 and 3, right? So those add up to what you see in that first list. So, that's kind of how it works. And what's cool here is that the 1 dot dot, Haskell just took what it needed, right? It has this constraint that whichever list is shorter, it'll stop taking values from the other one, right? That way you don't get this explosion of computations. If 1 is small, then you have no more elements to map up. So, it's safe. You can just say, hey, I just want an infinite list. And to keep with the syntax, there's another trick, right? I can say, 1, comma 1, dot, dot. So you can actually give steps in this infinite list. This is just a little bit of sugar that, they're giving you to express how you want to make this infinite list, right? And so if you look at the second value, right, it's 10 and 1, 11 and 1, 12 and 1. So it's not actually incrementing, it's just an infinite list of 1s. Yeah?
So if you did 1 dot dot and 2 dot dot, then you would actually get the explosion, right?
Yes, so don't do that. All right, so where does Haskell really shine? I mean, where does it spark and boom, right? So we're going to make a fire show. Well, fireworks extravaganza using Haskell data types.
Is this going to take 20 minutes or about 9 seconds?
We're going to explore all of this and more, right? So I'm going to say this is kind of complicated, but I think you guys can handle it, right? So a fire show. No, I didn't want to say fireworks, but fire show is an explosion type, and a duration, or it's a rest for a duration. You're just hanging out. Or it's a fire show sequenced with another fire show. So the one on the left has to be done before the one on the right. And we have the parallel fire show, where the one on the left is done at the same time as the one on the right. Okay. So, if you just want to have nice names for common values, you can just give it a type synonym. You can say, oh, I know it's an integer, but how about we give it a better name and call it a duration, right? So it's just a dir, right? And then, just like we did the Boolean, we had true or false. We're going to say that an explosion type is, one of these. It's a sparkle, a bang, a red, white, a blue, or a smiley face, right? So here's the San Diego fire show, right? So this is, it's got a lot of brackets, but you kind of want to look at it. Just pick, that first equals, right? And you see that there's an explosion on the left and there's an explosion on the right, right? And then you see that those are all grouped together. So those two together make one fire show. And then you see that equals all the way on the left, right? And then it's got a grouping next to it, right? And that grouping there is another fire show. Because for this to type check, everything left or right of these little operators has to be a fire show. So I'm telling you right now, this does type check, and it's correct, right? And so what I'm showing you is a bunch of fire shows being done in parallel. And, you're thinking to yourself, well, that might be kind of cool. So do you see the $125,000 problem? Right? So I just found that number. I'm not sure if that's exactly how much it costs. I think it might be more. But, that's quite a good show. But, all right, let's figure out how could we do some quality control on this. How could we look at that fire show data structure and really figure out how long is it going to last? So I'm repeating the data definition for you, and then we're going to write a function which can break down the fireworks display into, its overall duration. All right. So this is a really good example of type-directed programming. You know all the possible values for a fireworks show. You know that it could have sub-shows, or it could be resting, or it could just be an explosion, right? So we're going to take that data definition and start mapping it into all the cases of the function. So you get your explosion, we don't care what type it is, we just care about its duration. All right, cool. That duration is dirt, right? Cool. And then if it's a rest of a duration, that duration is just that value we pulled out, right? Now it gets a little bit more interesting. What if it is a, just a sequential show, right? Well, that means you have to take the time of the one on the left and take the time of the one on the right and then put them together, right? And, keep going. We've got the show on the left, show on the right, but if they're done in parallel, then you want to take the greater of the two. That's kind of how we're making our show. If you've got two fireworks displays going on, they go, but one stops, the other keeps going, we're going to measure from here to the longest one. That's how we're doing a parallel show. So it's going to be a little jagged in how it's done. But, here's how we do the greater of. Right? A little bit more syntax. There's a lot of ways to write what we're doing. But here, we're doing it using something called guards. Right? And so this is kind of cool, is that you can guard which of the statements on the right is performed by first inspecting the inputs. You can say, oh, is the left duration greater than the right duration? Yes, then left duration. But if it's anything else, then it's the right duration. Right? So a very simple way of choosing the longest one. Right? So, right, we're going to go back, take a look at the San Diego show, and it's a whole 10 seconds long. Right? And then, cool, let's go to Xavier's show. And it's actually a little bit longer, so I think people are going to like it. But, it was 10, right? And then it's 37, right? And all I changed, really, was those characters on the left, right? So there it says equal on the left. So it's putting everything in parallel. But on mine, there's a quick little fix, and I'm just like, oh, before we do this, how about we run the duration? Oh, I found the bug, I fixed it. There we go. Okay. All right. So in any language, you want to model your problem domain. So, functional modeling is value oriented. I just showed you that, I made this type, and it could only have, those 4 values, right? And what I said is that if it's going to be a fireworks show, it's got to look like this, right? And then Haskell tells me that if I can make like a computation that looks like a fireworks show, then it will let me compile it, and it'll be happy, right? So, right, recursive values, they're pretty cool. They actually worked out pretty well in this situation. So they're your friends, and they can get a little bit hairy sometimes, but you get some nice things to think about. And, there you go. All right. So, we talked a little bit about laziness before, right? And, you're kind of thinking to yourself, is the laziness of building these lists or building these fireworks, if Haskell waits till the last minute, is it worth it? What am I getting for it, right? So you have to think about balancing the runtime, doing all this bookkeeping on whether something has been done or not, versus doing work you don't need to do. It's kind of fun to think about. When you're trying to make better code in Ruby, you're looking for parts that are doing unnecessary work, right? That's a good spot to look. Are we iterating over this list unnecessarily? Are we not using all these values, right? Can we filter earlier so we can make smaller sets of data to work with later on, right? So, some Haskell guys must have broken into the Ruby source code, and they added some currying to it, right? So you can make a lambda that takes 2 arguments, right? X plus y, and it's got this weird syntax. I'm not totally sold on it. And you can say dot curry dot 0, and you're kind of like, you know, I can kind of guess what it does, right? It's putting the 0 in for the x, right? So essentially, when you pass it in a value, it'll just pass that value right back out, like the identity, right? So it's not quite idiomatic, but you can do it. So, you know, if you want to curry values, you can do that. So yeah, Haskell's a big subject. You know, I just showed you like pure computations, right? You may have heard hype and anti-hype about monads, right? And the I/O monad, and you know, how do you actually affect state changes outside of your Haskell program, right? But you know, unless you can do pure computations and you kind of get a handle of that, you're going to have a really hard time progressing much further. So you know, just give you a little introduction and you know, assure you that Haskell can do some real work. So you know, if you do want to explore these ideas, you can make fun little toy projects. And you know, just remember your goal, right? You just want to expose yourself to new ideas and kind of see where they'll take you. All right. Hey, thanks, Xavier. All right, any questions?
Okay, so I have a hypothesis about the syntax, but I wanted to see if I'm right or not.
Okay.
So I was looking at the function definitions when you have what we would think of as a function with multiple parameters. So like add, you would have x arrow, y arrow, z or whatever.
Yeah.
So obviously the last one is the result. But the arrows were kind of weirding me out. And is it because it's just automatically currying every parameter?
Yes.
Okay.
Right. So you know, I didn't show you how to make the literal lambdas. Right. So you know, in Ruby you can make a proc or you can make a lambda. You give it the parameters and you do that. But what actually happens is that these arguments all get folded into like recursive lambdas. That way, the outside can be applied and the inside comes out, and you just keep going. So yes, that's just about right. That's how you should think about it.
Okay. Thanks.
All right. Any more questions? Cool. Thanks.
Thanks, Xavier.